My name is Kenneth Oy. I'm a professor in political science and engineering systems at MIT. I also serve as director of the MIT program on emerging technologies. I also sit in a position that bears on the topic of today's commentary. I'm one of the faculty PIs in something called the NSF Synthetic Biology Engineering Research Center, where I work with engineering folks like Jay Kiesling, George Church, Drew Endy, Tom Knight, and others who are in the same broad field that Craig Venter and his group work in. Last week, something remarkable happened. The press coverage associated with the Craig Venter creation of artificial life has been truly astonishing. In some ways, the press coverage has been in excess of the magnitude and originality and seriousness of what happened. If you look at the cover of The Economist, this image from Michelangelo of God or man creating life has been used again and again and again with reference to this great discovery. The idea of someone sitting in Rockville, Maryland on the Rockville Pike, taking the place of the Almighty, reaching out and creating life forms, has captured the public imagination. So what I'd like to do is to work through several aspects of what actually happened and then work through some of the applications, some of the economic implications, some of the safety and security implications as well. So let's start, not necessarily with the Sistine Chapel, but with the discovery, and it is a significant and interesting discovery and development that came out of the Venter laboratories last week. In effect, what Venter did was something which is both less dramatic and more interesting than what much of the media attention has suggested. What he did was he took a garden variety, not particularly dangerous, in fact very, very benign microorganism. He took the sequence of that organism, put it on the computer, and made adjustments and modifications to the DNA. The adjustments that he made were not radically redefining or reshaping the characteristics of the organism. They were implanting watermarks that you could tell that it was an artificial beast, and little tinkering around the edges. What was remarkable was that after making these little efforts at redesign on the information on the characteristics of the genome, what Venter and his group then did was they synthesized the genome from scratch and implanted it in cytoplasm and created an artificial cell which has gone on, the organism has gone on, is self-replicating. It's reproduced. So what do we have here? On the one hand, what we have is something that is a logical extension of things that have been going on for a while. It's an incremental change. For many years, we've had logarithmic increases in the power of sequencing and logarithmic increases in the power of synthesis, the creation of DNA. And these two come together in this development. The sequencing in terms of getting the information on the genome of the organism. On the other hand, what you have is synthesis in terms of taking that information and translating it into a sequence, into the organism itself. We also have developments, again, incremental in terms of understandings that lead to the ability to redesign with some degree of reliability. So what do we have here? On the one hand, we have an incremental change. On the other, we have a breakthrough, the creation of an artificial life form. The reaction to this has been quite striking. I've been reading the press on this. I was asked to comment on the Venter discovery before it was published by Science magazine. And what has happened in terms of NGO responses and reactions and regulatory responses and reactions has been all over the map. The common position that I see again and again and again is that this radical change requires slowdowns, stops, halts in the development of the technology. And that's been one common set of reactions, largely out of Europe and out of some American non-governmental organizations, out of civil society. The reactions out of industry have focused very heavily on either, from Venter's competitors, this is no big deal at all, or from others, let's not encumber or slow down the development of a technology with tremendous potential for good. So let's sit back and try to get a sense of what some of the potential applications are and to get a clear sense of what potential dangers might be. In doing this, it's critically important to differentiate between the near term, the short term, the next couple years, and longer term considerations and prospects. If we look to the immediate, to the near term, I believe that much of the reactions have grossly exaggerated the significance of what has taken place. The organism itself was not radically redesigned and is quite benign. And what we have here is a demonstration of a proof of concept, a set of methods, with applications right now not being that radical, not being that unusual. And in fact, everything that Venner is doing now could be done using other methods and means. So what's the big deal? Well, the big deal is that over the longer term, increasingly radical redesigns of organisms will be taking place. And the applications will range from, I would argue, good to some risk of evil. On the good side, we have a heck of a lot of research taking place right now using more traditional methods of recombinant DNA work to create, for example, biofuels, the re-engineering of yeast, for example, to implant metabolic pathways, to be creating not just ethanol from sugar, which is what we're doing now, or from corn, but to be taking a variety of feedstocks and translating them into not just ethanol, but even diesel or better fuels. In the area of medicine, what we have right now in a number of areas are the creation of compounds using re-engineered bacteria with metabolic pathways to be creating isoprenoids, to be taking shortcuts around naturally occurring sources of supply, potentially at with greater access and lower cost. In the area of even sensing, there are interesting developments, projects taking place to be developing biosensors that could be detecting toxics like arsenic. And in an era and in a week when we're all sitting around thinking about the Gulf oil spill, one of the potential greatest areas of application might even be bioremediation, the redesign of organisms, microorganisms, to be breaking down complex organic molecules like petroleum, to perhaps come up with more environmentally sensitive and less toxic means of addressing things like the oil spill that we see taking place in the Gulf, or that we see in many areas where oil is being produced. So all of these are nice potential, these are wonderful possibilities. What are the risks? There are some risks associated with the technologies that Venter and others are developing. Let's talk first about economics, and then we'll move to biology and to security. In terms of economics, a number of groups have raised the prospect or the possibility that the Venter approach to the creation of life creates intellectual property rights, which then can be used to lock up and control the development and the diffusion of the technologies. So one of the questions that Science Magazine posed to me at the time that the article was still in the press was, does this mean that Craig Venter will become the Microsoft of biology? In my view, there is some risk of this, but it's not that likely. And there are a couple of reasons why. Greater concentration may be possible, but if you look to Microsoft and how they pulled it off, it was through a combination of what people call network externalities, how if some people are using it, the value to others goes up. We all use Microsoft Word because others use Microsoft Word. The problem here is that the specific network externalities associated with biological engineering are, in my view, not as great as what we see with reference to software. The benefits of using something that others are using just don't scale and don't have the same effect in this area as we see in information technologies. Another way that Microsoft managed to create a dominant position, locking things up, was through protocols and standards that were proprietary. And then if others wish to interact with Microsoft technology, they're in a sense forced to be using Microsoft software. The irony here is that the Venter approach to synthetic biology in some senses weakens or diminishes the significance of protocols and standards and modularity relative to the work of people like Tom Knight, Drew Endy, and others. Basically, they're talking about doing it from scratch. You come up with a sequence, a set of instructions, and create the whole organism, the whole genome from scratch, instead of piecing it together with standard protocols and interfaces. So in a funny way, what these guys are doing is moving towards design on the one-up rather than methods which would be calling for and requiring coordination and standardized interfaces. The final point would be on property rights and intellectual, the role of patents. And there have been a series of developments that diminish somewhat the likelihood that Venture will be able to ride patent monopolies into a world of Microsoft. There was a court decision, Supreme Court decision called KSR Teleflex several years ago. That court decision really bore on the issue of how much originality is required in order to receive a patent. And it has had the effect of diminishing the patentability of a number of developments in this area, in areas where the logical next step is what is being patented, and such is the case here. There was also a case, Myriad Biotechnologies in Chicago, about a month ago, that really addressed the issue of how much patenting of DNA would be possible. And that decision, although not affirmed by appellate courts in the Supreme Court yet, does have the effect of reducing somewhat the ability of people to ride patenting strategies to dominance. Finally, Venture himself and his group have filed for patents quite aggressively in the past few years. The U.S. Patent and Trademark Office has basically turned down the claims on two of the most prominent patent applications that they filed a couple years ago. So for all of these reasons, there is reason to be worried about antitrust and competition issues, but I don't see an immediate move given these developments towards the creation of a new Microsoft in the area of biotechnologies. Now finally, let's turn to concerns over safety and security. A coalition of non-governmental organizations, including Friends of the Earth, ETC, and others, issued a statement 2 days ago calling for, or noting that there was a dearth of regulation of developments in this area, and calling for really much more intensive regulation before these technologies are developed further. So what are they worried about? In fact, over the long term with radical redesigns, I do sit back and believe that we should be looking ahead and seeking to anticipate safety and security and environmental implications of some of the applications and technologies that will be developed. You take something like bioremediation, and if you move immediately to bugs that are capable of breaking down petroleum, you know, the issue of where they would go, what effect they would have on naturally occurring, on wild types in the ocean, but also even on petroleum reserves is something that you'd want to be worried about. So the question is not, should there be attention to biological risks and environmental risks, but how should that attention be focused and what form should it take? To me, what I find most striking here is the tremendous uncertainty associated with the categories of applications that are coming down the road and with the appraisal of the risks associated with them. Under conditions of complexity and uncertainty, where we're not quite sure what's going to be happening, we don't have a lot of the information that would be useful to have up front right now. The technologies have not even really been developed, the applications are not in hand, and the environmental effects are not well understood. What I would call for would be much more scrutiny and monitoring of the technologies as they develop, with systematic attention to gathering the information that is needed to be doing the profiling of the risks, to be feeding that information back in, to be designing hopefully safer versions of the organisms, building in containment so that horizontal genetic exchange would be limited or survival would be unlikely, for example, on accidental release. And so the position that I take is a little bit different from the standard industry line of let 1,000 flowers bloom of varying colors and genetic backgrounds, or the NGO position of maybe it's time for a moratorium. I believe that the technology should be developing, but with far more in the way of information gathering and oversight than is the case now, without necessarily shutting down, in fact, without shutting down the development of the methods that have such promise. Finally, there's the issue of security. Some of the commentary that I've seen has really focused on the specter of terrorists acquiring biotechnologies and modifying wild types to make them even more ferocious, synthesizing Ebola or synthesizing smallpox, modifying them to make them even more fearsome than they are now. And people are quite creative. We have a system of material controls that limit access to smallpox. And if the sequence is known, then methods of sequencing and synthesis can allow the reproduction of the dreaded disease, even without access to stocks of smallpox. Or if you turn to Ebola, some have talked about making it slightly less dangerous so that it doesn't kill people quite so quickly, which would increase the rate of spread, or re-engineering bugs in manners and in ways that would make them more selective. These threats are perhaps in the future. Access to the technologies that would be required to do terrible things is at present somewhat limited. The Venter approach to synthetic biology, in my view, takes a lot of equipment, a lot of work, is not readily accessible. Something to worry about over the longer term, but the good news is that it's not that your garden variety hackers or terrorist groups are sitting around with the equipment and the access to be able to do these things now. We have time. Time to do what? To be gathering information and devising more effective systems of control and regulation that can protect a legitimate public interest in security without necessarily stifling a technology that does have promising applications. The bottom line is that this is a remarkable accomplishment that's worth tracking, and I have enormous respect for the group that did it. The bad news and good news is that the short-term benefits and risks are limited. It's a short-term benefit in terms of potential security and biosafety issues emerging with force later and not immediately. It's a cost because some good things that could come down the road in terms of applications are not quite mature. At the same time, the long-term significance of developments in biotechnologies in general, Venter being part of a larger picture, are enormous. In the past, emerging technologies often have enormous effects that are not understood at the times that they're created. And it's these long-term, larger-scale implications, positive and negative, that are the most interesting. And the good news is that we have time to do the work necessary to be managing risks, acquiring information, and responding in a manner that I think makes sense. It's not as dramatic as a shutdown, and not as dramatic as let 1,000 flowers of varying colors and genetic heritages bloom. But this is where I think that we have to be going in terms of public policy.